Hello, class. Today we're going to continue with domain of logarithmic functions. And basically, now that we know how to transform functions, we can see from the graph what the domain is. But what if you don't have the graph? How do you find the domain? So I'm going to use an example from a transformation problem and then kind of get into the nitty-gritties of finding the domain of a logarithmic function. So say I have this function here, f of x is equal to 2 log 5 x minus 2 plus 1. Well, clearly my base function is log 5 of x. All right, now let's see how the set of transformations leads us to arrive at what f of x is right now. So clearly you can see that there's a horizontal shift to the right. So I get log 5 of x minus 2. So it's a horizontal shift to the right by 2. And then there was a stretch by a factor of 2. So you get 2 log 5. So it's a vertical stretch by 2. And then finally we moved it up. So it's 2 log 5 x minus 2 plus 1. That's a vertical shift up by 1. So we see the sequence of transformation. Now let's use that to help us figure out what the graph should look like. So from my base graph, let's see if we can locate 2 points. One point is obvious to us. That's 1, 0. The other one, since the function is log 5 of x, my base function, we can see clearly that if x was 25, 5 raised to the 2 gives me 25. So I can use 25 over here, which gives me 2. All right, so the graph kind of looks like something like this. That, not forgetting that we have a vertical asymptote at x equal to 0. So this is 25, 2. So at least with 2 points, we can move things around, okay? So now let's use the information we have on this to see what we can do. Clearly, the vertical asymptote, we started off with x equal to 0, and it gets shifted horizontally by a factor of 2. So the horizontal asymptote moves to become what? X is equal to 2. If I take the point 1, 0 and I walk through the transformations, it first was shifted to the right by 2. So the new point is 3, 0. It got stretched by a factor of 2. So the y gets multiplied by 2. So you still get 3, 0. And then it was moved up by 1. So that point becomes 3, 1. If I look at the point 25, 2, that gets moved up 2 places to the right. So that gives me 27 and 2. It gets stretched vertically by a factor of 2. So the y gets multiplied by 2. We get 4. And then it's moved up by 1. So now the point is 27, 5. So with that information, I can easily sketch this graph. I get my 1, 2. So I get my vertical asymptote that moved. I have 6, so 2, 3, 4, 5. Let's say 6 is somewhere here. And then let's go put 27 somewhere there. So I get 1, 2, 3, 4, 5. All right. Why am I using 6? It's supposed to be 3, so 3 is somewhere here. Okay, so 3 and 1 is there, and then 27 and 5. 1, 2, 3, 4, 5 is over here. So the graph looks like something like that. Okay. Clearly, this is not drawn to scale, but you'll get the idea. So, one thing we can do from the graph is, from the graph, we can clearly state what the domain is. What's the domain? The domain is x belongs to 2 to what? Positive infinity. So now the question is, if you hadn't drawn this function, how would you respond to this question here? Find the domain of 2 log 5 x minus 2 plus 1. I want you to find the domain. So to do this, let's do a little reflection on what the graph of a logarithmic function is, a to the x. So the graph of a to the x has a vertical asymptote, and then it's passing through 1, 0. So the graph looks like this. And its domain is x greater than 0. So we have a basis to fall on to determine what a domain of any logarithmic function should look like. From the base function, which is f equal to log a of x, the domain is always all positive numbers. All right, so I'm looking at x greater than 0. So I'm going to take that information and go over here, because we've seen that a log function can never be negative. So whatever I have in my log expression, I'm always going to look to the argument. In this case, my argument is x minus 2, and I want to make sure that it obeys the rules of what a log function should look like. That means that the input should always be greater than 0. In this case, I'm going to set x minus 2 has to be greater than what? 0. So here I end up with x greater than 2, so I know that the domain is x belonging to what? 2, what? 2, infinity. So our plan for finding the domains of logarithmic functions are, we're going to always take the argument and set it equal to what? Set it equal to set it greater than 0. So I want you to think big picture. Remember, we did combining functions last term. So if I have 2 log functions that have 2 different arguments, I would have to find their domain and intersect them to find the domain for the function. So all those things come into play. All right, so let's look at a quick example. Over here, if I have f of x is equal to log 2 of x minus x squared minus 4. All right, that's my function. So to find the domain, I need to set x squared minus 4 greater than 0. Well, to do this, I rely on my experience from 330 to help me solve this. So here I can put it on the number line. My factors are, or my zeros are 2, -2, and 2, and I'm going to check to see where this equality is true. So if I pick anything bigger than 2, test the value bigger than 2, you can clearly see that this is positive. If you pick anything between -2 and 2 and you plug it in here, you can clearly see that if you pick 0, the outcome here is negative. If you pick a test value from -2 to infinity, say if you pick -5, then you get negative times negative, that's positive. So I know that the domain is going to be in this region, anything from negative what? Negative infinity to negative 2. And then this other region here from 2 to positive infinity. So the domain is going to be from negative infinity to negative 2 union 2 to infinity. Let's look at another example. I have f of x is equal to log 6 of x squared plus 5x plus 6 plus log of 6 to the x minus 7. That's what I have, and I want to try and find the domain. So I can see clearly that if I set the first one, x squared plus 5x plus 6 greater than 0, I get x plus 3, and x plus 2 has to be greater than 0. So if we plug this on the number line, we have negative 3, negative 2. If I pick a number greater than negative 2 going, then you can clearly see that this is positive. If I pick a number that is between negative 3 and negative 2, we see that that is negative. And then when we pick anything between negative infinity and negative 3, that's back to positive. So I'm looking at the domain for the first log function to be negative infinity to negative 3 union negative 2 to infinity. But if I look at the second one, that's x minus 7 is greater than what? Greater than 0. X has to be greater than what? Greater than 7. All right, so that's fairly easy. So now if we combine the two, so I'm doing the domain of that intersection x greater than 7, then what is the answer to this? It looks like the answer is going to be from negative infinity to, well, let's set it up and let's do it on the number line. I like the number line. It makes things clearer to everybody. So on the number line, I'm going from there to negative 3. And then I'm going from negative 2 all the way there. And then the other one says I'm at 7. And I'm going that way. So for me to combine this together, you can clearly see that if I combine things together, the only places where I could put things in is what? Right here. That's the only place where they both share the same information. So the domain for f of x would be x greater than what? Greater than 7. Okay. All right. So that is it for domains of logarithmic functions. All right. I will see you in the next video.